Hello again and welcome to Advanced Physics for High School Students. This is Lesson 26 with Projectile Motion. I'll start with a short video clip that I think speaks for itself.
伊藤さんは発射の準備を始めた。15本の特大ペットボトルを発射台に装着。伊藤さん曰く、15本のペットボトルをいっぺんに発射させれば、必ず安定した推進力が得られるという。しかも、伊藤さんの計算では、10メートルは飛ぶというのだが。この浮き袋、浮き輪、そういう感じなら出ますか？泳げない伊藤さんのために、万全の準備は整った。そしていよいよ、3、2、
So I think that purports to be an example of projectile motion. I happen to think that video was faked, but nevertheless I thought it was kind of entertaining. Now I'd like to show you a few examples of projectile motion around here in Chattanooga. These are familiar scenes from Ross's Landing. These water jets, if you think about the particles of water, are examples of projectile motion. Here's one from the Art District. Ross's Landing again, very beautiful, artistic. And Coolidge Park. All of these are examples of projectile motion, motion in which there is only the object's weight which is acting. When we deal with projectile motion, we're going to be most frequently working with the equations of motion under constant acceleration. We're going to have horizontal equations and vertical equations. For projectile motion, the acceleration in the x direction is going to be 0, but I've written the x equations of motion out with acceleration shown because there are going to be some times when we deal with types of motion in which the x acceleration is not 0. And then the y equations over in green, the acceleration in the y direction is going to be 10 meters per second squared in the downward direction for projectiles. What we take our direction of positive motion to be depends usually on the initial conditions of the problem. What we want to do is to solve problems that involve projectiles, and our technique is going to be to break any vectors into horizontal and vertical components, consider each component independently, and then tie them together through the time t variable that appears in both equations. So let's take a look at the examples that are in your textbook. 26.1. A rock is thrown horizontally from a cliff that's 40 meters high. Its initial velocity is 60 meters per second. A. Determine the range or the horizontal distance from the cliff. And B. Determine the velocity, the speed and the direction as the rock strikes the ground. So here's the picture. I'm standing on the edge of this cliff. I've got a rock that I'm going to throw horizontally, that's key, at 60 meters per second. And I want to figure out where the rock's going to land, in other words, how far away from me horizontally the rock's going to land, and how fast and which way the rock is going right before it hits the ground. The rock's going to follow a parabolic path. At each point along the path, the velocity is going to be tangent to that parabola. So I'm going to show that velocity at various points along the path. And in part B, we want to figure out at the point right before the rock hits the ground, what is the magnitude of the velocity and what angle does it make with respect to the horizontal. Now, how do we do this problem? Well, first of all, look at what we know and to break it into horizontal and vertical lists. That's how I like to solve these problems. So I'm going to write down a horizontal list of things that I know and a vertical list of things that I know. I need to choose a coordinate system, and I need to choose a positive direction for that coordinate system. I like to put the origin of my coordinate system wherever the action begins. And since the action begins up at the top of the cliff, I'm going to let that be the origin of my coordinate system, where x is equal to 0 and y is equal to 0, and we're going to call that the initial position. I have horizontal variables, and I'm going to say that the initial position of the object horizontally is equal to 0. X naught is 0. And vertically, y naught is going to be 0 as well. V naught is 60 meters per second at 0 degrees because the object's thrown horizontally. So that means that there is an initial x component of the velocity that is 60 meters per second, and an initial y component of the velocity, v naught y, which is 0 meters per second. I'm going to let the direction of the initial motion be the positive direction. So for x, positive is going to be to the right. And for y, since there is no initial velocity in the y direction, I'm going to take the direction of the acceleration, which is the downward direction, to be positive. With that said, I can say that the acceleration in the y direction is plus 10 meters per second squared. And since this is a projectile, since weight is the only force that's acting, the unbalanced force acting, then the acceleration in the x direction is going to be 0. The object eventually is going to land right over here at that spot. I know that the y component of that point in space is plus 40 meters. And I'm looking for the x component. I don't know what the x is, but I do know y is plus 40. And what am I trying to find? I'm trying to find the range, for one thing. In other words, what is x equal to? And I'm trying to find what is the vector velocity, v. Those are the things I'm trying to find. Let's start with the x. I could figure out how much time that the object is in the air. I could figure out what x is because I know what the horizontal velocity is. I could use the second equation of motion in x. And I could say that there are certain things in this equation which are 0. The origin, the initial position, and the acceleration. Which means the equation becomes x is equal to v naught x times t. So if I could figure out a number for the time, then I could get a number for the range, x. How can I figure out the time? I have some information in the y equation. I know where the object starts at the origin. I know how fast it starts vertically, 0 meters per second. I know what its acceleration is, and I know when it hits the ground that it will be 40 meters away from where it started. I could use the second y equation to figure out the time from that. Here's how. In this y equation of motion, the initial position is 0, and the initial y velocity is 0. So there are some terms that drop out. And I'm left with an expression for y in terms of the acceleration and the time. I could figure out what the time is based on what the object is doing vertically. And that time that the object's moving vertically is going to be the same time that the object moves horizontally. With your permission, I'll do a couple of steps of algebra. And now I want to put in some numbers. I know that the acceleration is plus 10 and the y position is plus 40. So I'll feed those in. And I find that the object is in the air for 2.83 seconds. With that in mind, I can go back to my x equation and put in that 2.83 seconds and figure out what the range is. So over on the left-hand side here, I've written with the numbers, and I'll put those numbers in. And I get that the object goes nearly 170 meters away from where it started. So in our picture up above, this distance between the base of the cliff here and where the object hits the ground is nearly 170 meters. Now we're ready for part B. What is the vector velocity? The vector velocity is made of a horizontal part and a vertical part. If we go back up to our picture here, we can see that the horizontal part, we're going to call that Vx, and the vertical part, we're going to call that Vy. So I have a velocity triangle. And if I could figure out what the legs of that velocity triangle are, then I could use the Pythagorean theorem and a trig function to figure out the hypotenuse and the angle. How am I going to do that? The way I'm going to do that is I'm going to use the second equation of motion along with the time to figure those things out. Let me redraw the velocity triangle. And there's a relationship between the instantaneous velocity, the initial velocity, the acceleration, and the time. There's a vertical equation and there's a horizontal equation. Horizontally, the acceleration in the x direction is equal to 0. So that term disappears, and I have that the horizontal velocity at any instant in time is the same as the initial horizontal velocity, which in this case was 60 meters per second. So I know one leg of this triangle already. To figure out the y part, I use the acceleration and the time along with the initial velocity in the y direction, which they told us was 0. So I can put these numbers in and solve for the y component of the instantaneous velocity. And I'll feed in the numbers, and that's something I can do in my head. I get that the vertical component of the velocity at the instant right before the object hits the ground is going to be 28.2 meters per second. Now I've got it. Pythagorean theorem and a trig function to figure out the angle. I'll do that just quickly. So there's the Pythagorean theorem, and now we'll feed in the numbers. So I get the hypotenuse of this velocity triangle is 66.3 meters per second. And now I've got to work on the angle. I'm going to use the tangent function. The tangent of the angle theta is going to be the y component of the instantaneous velocity divided by the x component of the instantaneous velocity. So I can take the arc tangent of both sides, put in the numbers, and I'll get some angle. And I get that the angle is just over 25 degrees down from the horizontal. So that solves this problem. In part A, I found that the range was 170 meters roughly, and in part B, I found that at the instant right before the object hits the ground, it's traveling at a speed of 66.3 meters per second at an angle of 25 degrees below the horizontal. That is the first example.